Welcome back to Concurrency. I'm Daniel, and in this video we are going to explore parallel collections in Scala and a host of some other utilities in Scala and on the JVM. Now, in the IDE, I want you to create a simple Scala application under the Part 3 concurrency package by right-clicking New Scala class, and let's create the parallel utils application, make this an object, and of course make it extends app. Now, there are two big things that I want to talk about in this lesson. Topic number one is parallel collections. And the way that we create parallel collections in Scala is super simple. Let's say we have a parallel list, which we can parallelize by saying list 1, 2, 3, which is a sequence or a serial collection, and we just call the par method. So .par transforms this list into a parallel version of the list. A parallel collection means that operations on them are handled by multiple threads at the same time. The way that we create a parallel collection is either by calling the par method on a serial collection, or we can instantiate a parallel version of our collections by hand. So if we say, for example, a par vector, we can simply say par vector of int. Of course, we need to import it, and that should be it. Or we can simply pass in some collections. And we've created a parallel representation of a vector. Now, we can create parallel versions of collections including, but not limited to, sequences, vectors, arrays, maps, sets, including hash sets, trisets, and for map as well, hash maps, tri maps, and many more. And in general, parallelizing collections leads to increased perf. So let's write a small utility method. I'm going to call this measure, which returns the number of milliseconds that an expression takes to evaluate. So let's say we have an operation which is of type by name t, and let's add the type parameter here. And this will return a long as the number of milliseconds that this operation takes to evaluate. And the way that we are going to measure the operation is going to be very simple. I'm just going to call it time by system.current time millis, and then I'm going to just call or use operation, which will force it to evaluate, and then I'm just going to return system.current time millis minus time. Not the perfect benchmark, very simple. And say we want to measure how much it takes for us to process a big serial list versus a big parallel list. So let's say we have a small list, which is, say, 1 to 10 million elements. Just call it toList. And let's call this serial time of measuring. So measure, and inside I'm just going to say list.map, and assuming I'm incrementing all the elements by 1. And the parallel time is going to be measure with list.par.map, and the same function. So let's print these out. So print line serial time is serial time, and the same for parallel. Parallel time plus parallel time. And let's see this in action. So running this, compiling, and we're on. It's going to take quite a few seconds to process 10 million elements, but we do want to measure significant performance improvement by parallelizing a list. So we should be seeing just a few seconds to process the serial list and roughly half or probably less, then okay. So we have 6.3 seconds basically, and 3.4 seconds for parallel. So the par version apparently does better by roughly a factor of 2. Actually, let's move this print line statement above here so we can see when the serial time has finished running. And let's decrease the number of elements, like from 10 million to 10,000, because we're going to see some interesting results. So if we decrease the number of elements from the list to 10,000, we have serial time 4 and parallel time 71. Now, can you think of why that might happen? Now, if you've done parallel programming before, you know that starting and stopping threads is actually pretty expensive compared to the time it takes for a single CPU to process a small instance of a collection. So in practice, for small instances of collections, it's actually cheaper to keep them serial rather than parallelizing them. That's because parallel collections operate on what is called the MapReduce model. So say we want to apply an operation on a parallel collection. Now, what a parallel collection will do is it will split the elements into chunks, which will be processed independently by a single thread. This is done in the Scala parallel collections library architecture with a thing called splitter. Then the actual operation takes place on each of those chunks, and every chunk is processed by a separate thread. And then the results are combined together. So recombine. This is called the reduce step with a thing called combiner. Otherwise, the parallel versions of our collections should be used in the exact same way as sequential collections, in the sense that they have map, flat map, filter, for each, reduce, all that kind of stuff, fold. But be very careful with some of these operations. Like map, flat map, filter, and for each are pretty safe, but reduce and fold are not always. So let me give you an example. If we have, let's say, print line list 1, 2, 3, reduce, and the operator is minus in between two operands, and print line list 1, 2, 3 par reduce with the same operator, then we will get different results. So if I right click and run this, you see that the serial result is -4. That's 1, -2, -3. They're processed in order, but because we've parallelized the list 1, 2, 3 in the second case, we can't guarantee that the result will be -4 because we don't know the order in which the operands will be brought in. So be very careful with fold and reduce, because the operators that you might pass to them, the functions inside, might not be associative. And in the case of parallel collections, these might yield different results than the serial versions, and you may not want that. Second problem with parallel collections is that sometimes you need synchronization. Not on the collections themselves, but on the results they act upon. So say, for example, I have a var called sum, and we just say list 1, 2, 3 par for each, and we say sum plus equals the element inside. This is a pretty innocent summing up of the elements of the list. And if we print line sum, we should be seeing the number 6. But that's not guaranteed, because when you say for each on a parallel collection, then you have multiple threads that might run this function, and the side effects might be computed in a different order, and they might be under synchronization or race conditions. So in our case, the sum might be accessed by 2 simultaneous threads at the same time, and the number 6 here is not guaranteed. If I run this a bunch of times, I might actually get into the situation where the number 6 at the end is actually not 6, but given that I have just 3 numbers, I'm probably going to almost always get the number 6, but that's not guaranteed. So pay very close attention to race conditions. Now, let's talk a bit about configuring parallel collections. Because when you say list 1, 2, 3 par, you basically relinquished any kind of control over how many threads, how the list 1, 2, 3 is actually managed by those threads, and so on and so forth. Now, configuring a parallel collection is done with a member called task support. So if I say of par vector dot task support equals, and we can pass in here a new thread manager in the form of, for example, a new fork join task support. And this guy receives a fork join pool with 2 threads. Just import. All right, and 2 here is the number of threads that are going to manage the parallel vector. Task support is an internal member of a parallel collection. So if I command click or control click, we see that we have a def task support as a getter and a def task support underscore equals as a setter for the task support member. And the underscore task support is the actual internal thread manager for this collection. Now, in terms of what you can put inside a task support, most of the time you'll need a fork join task support with a fork join pool with a number of threads. That's the most common case. As alternatives, you can use thread pool task support, which is an old version and it's now deprecated. It basically did the same thing as the fork join task support. There's also the execution context task support, which takes an execution context as a parameter. The execution context, if you remember, is the kind of thing that got passed to futures when you created those. So the parallel collections are in this way compatible with the futures API, especially if you want to create your own parallel collection and if you want to use futures inside. If you're feeling really advanced, you can create your own task support by saying a par vector dot task support equals new task support, the trait, and you need to override a few methods. So you need to override this guy, execute. You need to override execute and wait result. You need to override the parallelism level, and you need to also override the environment value. Once you have done that, your task support is a viable assignable object to your task support member of the parallel collection. Now, what does each method do? Now, execute schedules a thread to run in parallel, basically. Execute and wait result does the same thing, but it's going to block until a result is available. So it's basically going to wait for the thread to join. Parallelism level is the number of cores that this should run, like CPU cores. And the environment is the actual manager that manages the threads. That's why it can be any ref. It can be a fork join pool. It can be an execution context, which is a totally different thing. It can be anything you want. All right, so this is an internal member here that will manage your threads. Now, in real life, there's very, very low chances that you are going to need this special task support. All right, so in very, very special cases where you need some special thread management. So that's about the overview that I'm going to make in this lesson about parallel collection. The purpose of this lesson is to have you acquainted to them. We won't go too deep into how much faster parallel collections are because benchmarking depends on a variety of factors like the actual architecture the code runs on, the kind of JVM and the generated bytecode is, the data type in the collection, which is cache friendly or not, the memory management of your computing architecture, the garbage collector. So when we run a perf or a time measurement, don't take it too literally. Our benchmark is super simplistic, but more in the style of this thing generally runs faster than this other thing. So as we saw with the 10 million list collection, in general, the parallel list operates roughly 2 times as fast as the serial version. Now, having said that, the second big topic that I'm going to talk about in this lesson is atomic operations and references. So atomic ops and references. Now, just to be clear, before we start diving into the Scala and the JVM library, an atomic operation is the one that cannot be divided. Either it runs fully or not at all. So in a multi-threaded context, an atomic operation cannot be intercepted by another thread, just so that we're clear. Now, Java introduced atomic types which are thread safe. And of course, being on the JVM, Scala has access to them. So for example, if I say val atomic as a new atomic, and you see here a bunch of options: atomic log, atomic boolean, atomic integer, atomic long array. We are just going to use the very general atomic reference with type int. Let's just put in the value 2 inside. Atomic references, much like the other atomic types like atomic int, atomic long, atomic everything, have the property that they have atomic operations, in the sense that if I say val current value equals atomic dot say get, the get method, the extraction method, the read part of the atomic is thread safe. So when you extract the value inside the atomic reference, no other thread can read or write to this atomic reference. So this is a thread safe read. There's also a thread safe write by saying atomic dot set, and let's say we have the value 4 inside. This is a thread safe write. So notice that atomic references can be mutated in place. Now, they would be really poor if their whole API was limited to get and set. We have a lot of other operations that are also atomic. For example, if I say atomic dot get and set, say 5, then this will do a combination of extracting the current value of the atomic and setting it to a new value in a thread safe way. So thread safe combo. Then we have operations for comparing and setting for the situations when we say if x equals 42, then x equals 45. Something like that. And atomic can do that by saying compare and set, and we just say like 38 and 56. So what this says is if the value is 38, then set the value to 56. Otherwise, just do nothing. And this whole logic operates in one go in a thread safe way. Note that the comparing here does shallow equality. It means it compares reference equality. So it doesn't do deep equality inside. And finally, we can have functions running on atomic references. So let me give you an example. If we have atomic dot update and get, then this will set a new value inside with a function, and it will return the result of that function applied to the value that the atomic reference currently contains. So if we have a function like x plus 1, then this will update the value inside the atomic by running this function on top of it, and it will return the result in one sweep. So this is a thread safe function run. There's also a reverse version by saying atomic dot get and update, which will do the operations in reverse order. So it will get the old value, and then it will run the function on the value contained in the atomic reference. So we have update and get and update if you want to inverse the order of operations. And lastly, we have accumulation. So we have atomic dot accumulate and get, and this will receive, instead of a 1 parameter function, this receives a 2 parameter function and an argument. So say for example that I want to pass in the number 12 and the 2 function argument that takes the value inside the atomic, this parameter, and does something with them. So say for example I have the sum operator. So this will take the argument, take the value inside the atomic, sum them up, set the value inside the atomic, and then return the result in one go. This is called accumulation. And there's also, of course, a reverse version. So we can say get and accumulate. Again, with some kind of parameter and the binary operator inside. Alright, so we've learned quite a bit about Scala collections and about the atomic library on the JVM. I'm Daniel. I hope you liked this video and found it useful, and I'm looking forward to having you in the very next one.